I promised to make a video to talk about section 13.4 on curvature because this is a topic that is officially on the course syllabus, for the department for 251, but it's something that just kind of gets squeezed out in practice when I try to lecture. So I was going to make a video about it, and then there's a couple problems in the web assign for you to look at, and then that will be good. So the question here that we are thinking about when we're thinking about curvature is, how much does a curve bend? So just to draw some picture here, so I'm just going to doodle. So imagine that this is a curve, and I'm drawing on a piece of paper. Use your imagination that there's a little bit of three-dimensionality to it. So just to point out what we see here, so at a place like this, it's not bending much. But as we kind of go through some of these tight corkscrews over here, this is bending a lot. And so somehow we want to try to quantify this. And so we're going to quantify this through the notion of curvature. So here, this is going to, along in this stretch, this is going to have small curvature. And here we want the curvature to be large. So we want to think about how to measure this. A first attempt to think about this might be to think about, if we were talking about curviness, if you ask a Calc 1 student might think about f double prime of x. So remember, f double prime of x, this has to do in 151 with concavity. And so you might think that concavity is kind of like curvature. This might be something that you would think carries over to curvature. However, there's two problems with this. So problem number one is that it's not for functions in 3D. So if we're talking about a vector valued function with three, where the vector output has three components to it, we can't really talk about f double prime of x. That's not something that we could talk about. If we have we have y is equal to f of x, we could think about this, but it doesn't carry over to 3 dimensions. But even if we wanted to talk about this in, a y is equal to f of x sense, well, think about a circle, or I guess we could have the top semicircle. The top semicircle here with radius 1. If we were to compute the second derivative, we would see that f double prime of x is negative 1 minus x squared to the minus 3/2. And this is troubling because the second derivative here depends on x. And so the curvature here is going to be different than the curvature here is going to be different than the curvature here. You can find that just by plugging in different values of x and seeing you get different values for f double prime of x. So that's troubling, and that's, a circle, it feels like it's curving the same amount. I know I didn't do a very good job drawing this, but it feels like it's curving the same amount everywhere on the circle. So it's unsatisfactory. So we have a different definition of what curvature is going to be. I'm skipping the details of how we're going to come up with this. You can read the textbook to find it. So we're just going to cut to the chase. and say, let me hide part of this for the time being, which is if you have a regular parameterization, regular just means that the derivative is never zero, that if you're thinking about a particle moving, the particle never stops, then the curvature is given by the derivative, cross product, second derivative, all take the magnitude of that because the cross product is a vector. So take the magnitude of this vector and then divide the magnitude of this cross product by the magnitude of the velocity cubed. So it's a complicated looking formula. At the same time, it's something that you can just plop in. If I give you R of t, it's nothing, asking you to figure out the curvature is nothing more than asking you to do a large series of calculations, which is not difficult if you have the formula in front of you. And I'm assuming you'll have the formula in front of you. It is also worth noting that there's a special case here of if you do have a curvature of a graph, y is equal to f of x in 2 dimensions, we have this more simple version that's given here. So note the letter that we're using here for curvature is a Greek letter kappa. So kappa for curvature. Okay, so now that we have these definitions in our pocket, let's just go ahead and apply them without too much difficulty. So suppose now, let's start off with this first formula here. And so let's assume that I ask you about R of t is t squared, t cubed. And I say find kappa of t. So let's just take a look to see what we have here. We see we're going to need the first derivative and the second derivative. So let's go ahead and compute those. R prime of t is 1, 2t, and 3t squared. R double prime of t is 0, 2, and 6t. So here's our parameterization. Note that it's regular. It's never going to equal 0 because the second component of... Sorry, let me look at we're looking at R prime, not R double prime. So we should realize here that the first component is 1, so the overall vector velocity vector will never equal 0. So at this point, all we have to do is take the cross product, because we know that is a step we have to do. So we have to take the cross product of R of t with R double prime of t. So I hat, j hat, k hat, 1, 2t, 3t squared, 0, 2, 6t. Crunch, 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 I'll skip the details. This ends up as 6t squared minus 6t and 2. And so then at this point, to check what we need for the kappa, we see we need the magnitude of what we just found along with the magnitude of the velocity. So the magnitude of 6t squared minus 6t and 2. So skipping the details here once again you can check this for yourself. 36t to the 4th plus 36t squared plus 4. Take the square root of all of that. And we also need the magnitude of R prime of t. So magnitude of 1, 2t, and 3t squared. This is going to be the square root of 1 plus 4t squared plus 9t to the 4th. So putting all of these pieces together, kappa of t is this divided by the cube of this. So we're putting the pieces together. the magnitude here divided by the magnitude here cubed. So our final answer is the square root of 36t to the 4th plus 36t squared plus 4. So that goes there, that goes here, and now this goes in our denominator, and all of that cubed. Guess I could have written that expression to the 3/2 power would be a alternative and acceptable way to do it. So, moral of the story here, if I give you curvature and I say, find the curvature and you have the formula in front of you, I'm assuming that you have the formula in front of you. This is not a formula I expect you to memorize. It's nothing more than just doing a long series of calculations. So, slightly on the long side, I'm skipping details here, slightly technical. At the same time, it's just plug into the formula. So, nothing too exciting. Let's do an example of the curvature of a graph y is equal to f of x. So, here is an example. Let's take a look at f of x is x cubed minus 3x squared plus 4. So let's figure out what do we need here. It looks like we need the first and second derivatives. So we will quickly write out the first and second derivatives. F prime of x is 3x squared minus 6x. F double prime of x is 6x minus 6. So kappa of x is, let's remember the formula here, it's 6x minus 6 with absolute values around that over 1 plus the first derivative, 3x squared minus 6x, all of that squared, and we raise that whole thing to the 3/2 power. And so here is, again, if we want to figure out the curvature, it's nothing more than take a couple partial derivatives and plop into the formula. Again, not a formula I'd expect you to have memorized. I could ask you to compute the curvature at particular values for x, which would be nothing more than you plopping in values into x and seeing what you get out of here. It's worth noting that, let me just show, this is an example I stole straight from the textbook, because it was easy for me to do here, and now I can just show a picture here instead of having to draw this myself, that this blue curve here, this is our original function, and the green curve is showing the curvature. And so we can see here that, let's take a look at this stretch in here, on the blue stretch. This looks pretty straight to me. Well, guess what? The curvature is pretty darn close to 0 at that point. Where do we have big turns? Well, there's a big turn, and there's a big turn, and those turns, guess what? They correspond exactly to where the curvature is high. So this matches what our intuition should be. So hooray, all of that checks out. So those are the two main examples that I wanted to do here. I have a couple of wrap-up comments. First wrap-up comment has to do with circles. So suppose that we have a circle of radius r. So a parameterization of a circle of radius, but let me use here big R, would be r cosine t, r sine t. I'm writing this as a circle in the plane, in the xy plane. If you wanted to think of this in 3 dimensions, you could just tack in a third component. That's a comma 0 here. And of course, we should talk about the bounds on our parameterization is going to be 0 to 2 pi. And so if you do all of the calculation, so I will omit the steps here. This would be a good exercise if you wanted to work through. This. This is a very common example. In fact, you could work through it. It's also in the textbook as the very first example of the section. If you want to check your work, you end up finding that the curvature is equal to 1 over the radius, and this should kind of match what our intuition says, because, well, let me just draw 2 circles here. So here's one circle. Here's a second circle. So this circle, the purple circle, has a bigger radius. The green circle has a smaller radius. But it seems like if we're thinking about this as you're driving around a road, well, this one is a much tighter turn than the purple circle is. This is much curvier. The green circle is much curvier than the purple circle. The green circle has a greater curvature than the purple circle does, and so we see it's the reciprocal. A smaller radius leads us to a larger curvature, because the formula for the curvature is 1 over the radius. So that matches up with what our intuition should be. So that's it. That's a wrap-up comment. And the final rapid comment, I probably should have led with this. Oh well, I'll end with this. Is just talk about applications. So a couple of common applications of curvature. So a fun one would be roller coasters. So the curvy, how curvy can you get it? How big can you get the curvature? A larger curvature would correspond to a more thrilling, more exciting ride. Perhaps more terrifying ride if you're the sort of person whose stomach gets bothered by such things like mine does. But then you can kind of think about, well, if it gets too curvy, maybe if you're an engineer designing roller coasters, it's going to get unsafe. So it's something to think about. DNA. So DNA, of course, has the famous, double helix. Something that looks like this. How curvy is your DNA? I'm certainly not an expert on this, but curvature of DNA is certainly important to some biologists. I mentioned in the previous one, I'll end with this one, road construction. So let's say that you are building a highway, and so here is the highway, and you want an off-ramp to cross onto this road, and so your off-ramp is going to look something like this. Well, guess what? If you are designing the highway, you're some kind of civil engineer designing the highway, you're thinking about how curvy the road is, because the curvature of the road is going to affect, how fast could a car safely travel around that road. So think about, get off a highway. It tells you the exit ramp has a posted speed limit of you shouldn't be traveling more than 25 miles an hour on it. Well, guess where that's coming from? That's coming from the curvature of the road. That's how that kind of stuff is going to be determined. So a little bit of a long video here, but that is now you know everything that you need to know about curvature.